need to first understand our definition of precision. And we can state that the temporal resolution is a good proxy for the precision. And I have some intuitive examples to show why this is actually a pretty good metric. If we say that we have a temporal resolution of 5 seconds, there's a relatively low temporal resolution here, meaning you're able to correct yourself way less, and you'll be much off from the target. Compared to, say, the 1 second temporal resolution duration, you're able to correct yourself much more frequently, and you're able to be more accurate. So this leads to our hypothesis, which is that a lower decision temporal resolution will lose granular control necessary for optimally completing a task. And intuitively, why this hypothesis might make sense is that if your temporal resolution is too low, then you won't be able to have the necessary sort of resolution of decisions to correct yourself, and you'll lose granular control, which requires precise control. So to answer this, we're basically quantifying how the action frequency affects the performance. We train our policies on 3 different tasks, which is point maze, fetch reach, and android door. Where point maze requires the least precision, fetch reach is more precise, and android door is the most precise. And we sweep over frequencies of 5, 20, and 40 here, and we train 3 policies on each of these. And for here, it's good to clarify that frequency here I define as the number of time steps to apply an action before sampling a new action. So in this context, frequency does not actually mean, so let's say frequency of 5, we take 5 actions for every time step. Frequency in this case means that we sample a new action every 5 time steps. So under this definition, a higher frequency would have lower precision because let's say 40, you're sampling a new action every 40 time steps compared to every 5 time steps. And throughout the presentation, we will be using this definition of frequency. So here are the results from this experiment, and the black lines represent the reward to success rate. And I want to direct attention towards the middle graph right here and fetch reach stents, which in this graph right here, we beautifully prove our hypothesis. We show that in this graph, as frequency increases, our training starts to degrade over time. And if we take a look at the right-hand side, android door here, we show that the lower frequency of frequency 5 performs really well, and that the higher frequencies of 20 and 40 simply fail to complete the task. So these two both prove our hypothesis well. However, in point maze, we see that frequency 5 and frequency 20 perform essentially on par. And in fact, frequency 20 might perform even a little bit better than frequency 5 as it converges quicker. And then we see that frequency 40 does worse than all of them. And there's a pattern break right here. Why is it that frequency 5 and 20 perform well, but as we keep increasing the frequency, suddenly at frequency 40, it performs worse? Well, it turns out we not only want precise control. In this hypothesis, we say that having a temporal resolution too high causes the policy to be susceptible to this thing called the curse of horizon. And what the curse of horizon is, it is quantified in this paper called Horizon Reduction Makes RL Scalable. And basically what this paper is saying is that many RL algorithms fail to scale for longer horizon tasks, and hyperparameter tuning does not solve this problem. Now what the horizon basically means is that for a task, the horizon essentially is the time or the length it takes to complete the task. And essentially what this paper is saying is that if our temporal resolution is too high, we're gonna have to take actions much more frequently. And this inflates our horizon, causing the horizon to be longer and us to be susceptible to this curse of horizon. So this creates what's known as, or what I call the precision horizon trade-off. On one end, if your resolution is too low, you're not going to be able to complete granular control, or you won't have granular control necessary for completing a task. And on the other end, if your temporal resolution is too high, you'll be susceptible to this curse of horizon. So this leads to our other hypothesis. Given a specific task, there can be an ideal precision level. And this hypothesis right here might seem kind of trivial. I mean, of course, if you sweep the frequencies, we show that they affect training, so of course there's going to be some frequency that's ideal. Intuitively, you might expect the ideal precision level to look something like this. On one end it performs worse, and on the other end it performs worse, and it has this quadratic-like shape. And in the middle is our optimal. However, we show in our experiment that this is actually not so clear-cut. So we test on point maze and fragmentation, and we do a little bit of a more finer frequency sweep. We graph the max reward in the convergence time step. Convergence here simply means that at which time step does the reward gain become less than 5%. Here are the results from this experiment. And as we see here, point maze does indeed have this concave-like behavior. However, we see that in Franca Kitchen, which is a sparse reward task, we see that it has sort of this jumping-like behavior. And basically from this, we say that there's no clear intuition about the curve shapes in certain tasks. And we see that the specific task can affect this shape of the curve for this ideal precision. And we also conjecture that constraints of the learning algorithm can affect the shape as well. For this specific experiment, we only trained with SAT. However, in future experiments, we should train with more learning algorithms to really show that learning algorithms can also affect the shape as well. So, now that we have this part of the narrative, which is precision horizon trade-off, and now I want to move to unsupervised skill learning. And to understand unsupervised skill learning, we'll first go over what basic skill learning with behavior cloning is. And what basic skill learning does is we have an expert policy. This expert policy is simply a data set, and this data set is generated from human demonstrations. And we generate state action pairs with this. We use this expert policy to train the policy to imitate these state action pairs generated from human demonstrations. And we train this policy to learn skills from it. Unsupervised skill learning does something different, and it comes from this paper called Diane, Diversity is All You Need. And essentially what this does is it maximizes this different information theoretic objective called the mutual information. And intuitively, all this mutual information means is that it tells you how much can you distinguish your current state from the skill you are acting. And by maximizing this information theoretic objective, you're directly telling the policy to generate skills as diverse as possible and lead to diverse states. And we see from Diane here, it's able to generate diverse spider skills. Current new state of the art has been Metra and CSF. And what these do differently is for mutual information, all it does is it incentivizes the model to maximize skill diversity. However, under mutual information, there's no incentive to cover the states. And so these two, this state coverage right here, these two are essentially the same under this mutual information objective. Metra and CSF maximize this different objective called the Wasserstein distance. And intuitively, what this basically tells you is it basically just gives the model an incentive to not only maximize for skill diversity, but also maximize for state coverage. So we've shown and we've talked about this unsupervised skill learning. And why is this better than just standard imitation learning? Well, in standard imitation learning, let's say this is your skill space. We are constrained by our human demonstrations compared to if we use unsupervised skill learning. Unsupervised skill learning is able to discover diverse skills that cover the skill space well like this. Additionally, it's scalable to new tasks as you don't need to collect human demonstrations every time you use a new task. This next experiment is simply to reproduce current unsupervised skill learning results. So we test Diane, Metra, CSF, we plot the state coverage as well as visualize the skills. We test on ant, half cheetah, and humanoid. And the results here, we see that Metra and CSF are able to greatly cover the state space. And the state space here is simply XY for anti-humanoid and the X position for half cheetah, since it's a 1D environment. And we see that Metra CSF are able to greatly cover the state space more than Diane. And when we visualize the skills, we see that Diane is able to learn diverse skills. However, most of the skills are pretty stationary and don't cover the state space a lot. Compared to Metra, which not only also learns diverse skills, but is also able to cover the state space, as you can see from this. This is the same case with CSF as well. So, we've shown that unsupervised skill learning has good results. How can we actually make use of the skills we learn in unsupervised skill learning? This leads to number 4, which is hierarchical reinforcement learning. And to quickly recap what hierarchical reinforcement learning does, we first train this low-level worker policy. What this low-level worker policy does is, intuitively, all it does is it takes this variable z and maps this variable z to a specific action. And we train this separately. Once we have this low-level worker policy, we train this separate meta-controller policy, which you can think of sort of as a high-level planner. And this meta-controller policy learns to select which z's are appropriate for the low-level policy to act on. And a very good analogy for this is, say you have a sport. The coach of the sport, let's say ping pong or whatever, would be the meta controller, telling you what to do. And the player would be the low-level controller, actually executing the skills. And typically in hierarchical reinforcement learning, the low-level policy learns skills. It learns to take in latent vectors, which represent a specific skill Z. And these skills can be anywhere from pushing, running, and grabbing. So, this next experiment, we will quantify how does the precision affect performance in under this hierarchical reinforcement learning set. Before, we only had action frequencies. Now we have actual skills we trained from unsupervised skill learning. We test this on the environment and maze, and we use the metra and skills we learned. We do a frequency sweep over 10, 25, and 40. And in the official paper, 25 is their ideal frequency. So this is the results. And we show that the precision horizon trade-off is still relevant in this case. And in fact, we see here that 25 is not optimal, and in fact, frequency 40 converges better, and it seems like it will do better. And it seems in this specific curve right here, we see this is more on the curse of horizon side of it, as it seems like the policy is preferring more higher frequencies. So we also show that the choice of frequency does indeed affect training under this hierarchical reinforcement learning context as well. So the takeaways and future work from this. The takeaways from this is from the precision horizon trade-off, we show that there indeed exists this trade-off between low and high frequency. You don't want a precision too low, as then you won't have granular control, and you don't want a precision too high, as you'll be susceptible to this curse of horizon. We also show that there's no clear intuition about the ideal precision of, I suppose it says concavity, but basically there's no clear intuition about the specific shape of the ideal precision. And we show that this is still relevant under hierarchical reinforcement learning context with learned skills. So future work. So the first future work I will do is unsupervised skill learning for fixed skill length. How are we supposed to do unsupervised skill learning to learn skills of fixed length? Maybe there could be new formulations, possibly new architectures, and probably the most promising one is we could just fix the specific episodes used when training unsupervised skill learning. I also want to mention that given the statements we made about ideal precision, we can argue that for a given composite task and learning algorithm, there can be an ideal set of precision levels. And the reason why this should be intuitive is that let's say you have a composite task of putting a box on top of a shelf in a room. A composite task can be made up of multiple subtasks, such as walk over to the box, grab a box, walk into a room with a shelf, and place the box. And subtasks such as walk over to the box would require a much lower precision compared to grabbing a box, which would require much higher precisions, such as precise finger movements. So, see that composite tasks could have ideal sets of precision levels. Then our second thing we'll do is to come up with maybe some kind of unsupervised skill learning algorithm to learn skills with multiple precision levels. And that is my work.
Anyone got any questions?
Edward.
Can you go back to the slide comparing the frequencies for the point maze and the kitchen tap? What does the frequency of 0 mean here?
Oh, that's frequency of 1. That's a graphical issue.
And also, what exactly is the kitchen task?
So the kitchen task is the kitchen task actually is a composite task. The kitchen task is essentially, you have a bunch of tasks such as turn on the lights, open the microwave, put the kettle, and this is a sparse reward task, meaning every time you complete a task, you get 1 reward. If you don't complete it, you get 0 reward. And my purpose of choosing tasks of point maze and Franken kitchen is to have diverse and different types of tasks, so I can really quantify the shape of this ideal precision.
Okay.
Alex.
Wait, I see in the, almost all of your graphs, it's it starts the y-axis is the reward.
Yes.
Does high reward always mean the task is completed or no?
So high reward may not always mean the task is completed. However, in my work, I did render out all of them. I don't have it in the slides here, however, I rendered, like, I visualized all of how they completed the task, and I can confirm that they do complete the task. So although higher word in other contexts might not mean it successfully completed the task, in my context, in my work here, it does. Aston.
So in your like previous non-hierarchical RL examples, the higher frequencies in the simpler tasks worked much better and compared sometimes better than the lower ones. But as the tasks got more complex, lower frequencies were the only ones that succeeded.
Yes.
Have you tested similar like complex tasks for your hierarchical RL, or do you plan to do that in the future?
I plan to do that in the future. I had because for the skill learning algorithm of Metro, it actually takes quite a long time. So I was only able to use what I had, like existing stuff I already had, which is I already had ant skills. In the future work, I would also train skills for the more precise tasks, such as Franca Kitchen or the door task I mentioned. Kelly?
To go back one slide. Wait, another sentence, sorry. This one, right? So, earlier we established through your test that like, lower level of frequency would perform better. But in this case, you said that they established that the frequency of 25 was best. Is there like an intuitive explanation for why the lowest frequency wouldn't always work the best?
So the reason why the lower frequencies wouldn't always work best is, so under my definition of frequency here, a lower frequency would mean a higher precision because you sample the skills much more often. But in one of our hypotheses, we've shown that this is susceptible to the curse of horizon. And essentially what this means is that if your precision is too high, you sample your task way more often, which increases the skills or the task's horizon, which is essentially the length it takes to complete the skill. And in the paper, horizon reduction makes RL scalable. We state that if our horizon is too long, RL fails to solve the task. Alex?
I see that like the curse of horizon suggests that with too small when its frequency is too small, the search space could get much larger. But what if you set intermediate goals, which then shrinks the search space? Wouldn't that help you with a lower frequency?
I think when you said set intermediate goals, I think that is analogous to curriculum learning. I'm pretty sure, where you learn like the easier task and a harder task, similar to what Somian presented with the curriculum learning. Yeah, that could be an interesting direction and would be future work I would explore. Cooper.
Can I get the visualizations of the learned skills, like Metro and the rest? Yeah, sure, Metro, I think. Can I see the bottom one in particular? Okay. So we are trying to learn diversity of skills in all of this, and these are cherry-picked examples, presumably. Those look awfully similar. I think same with the next one, the CSF one. CSF, I think is the name of it, right? It looks, so there's clearly diversity in the middle one, in the half cheetah, but it looks like there isn't very much diversity there. Can you explain why they would be so similar here?
Yeah, so for Metra and CSF, I guess the main contributions for Metra and CSF is that they also include the state coverage. And however, I think the main point is that the specific task of humanoid, I think humanoid itself is simply just one of the harder tasks to solve, and which is why the skills that it tried to generate were not as diverse. However, and although the actions specifically were not that diverse, we see that the end skills itself have some diversity in them.
Okay. Yeah, I think if I remember right, the Diane looked more diverse than the previous one for the human.
Yeah.
So it, to me seems at least that there's because I think it sounded a little bit like Metro and CSF were sort of objectively better, but it does seem that there is a trade-off of maybe convergence to diversity versus state coverage. It seems like it's not just one is objectively better for that combination. And would you agree with that?
Yeah, that seems like an interesting idea. I could test is the state coverage and diversity trade-off.
Yeah. It just seems that way. I was just asking you.
Edward.
Can you maybe go to one of the training curves,
Which one?
or just any one of them? Okay, sure. So I see in this one, whichever one seems to be the highest at the end also starts out to be the best one. Is there a reason they don't like instead start out at the same reward because they start out with random parameters there?
So in these training curves, what I actually truncate what's called the learning stubs. And in SAC, basically, there is this hyperparameter called learn starting. And basically what this hyperparameter says is, in SAC, you need to first collect experiences before actually starting to train. So what I truncate is basically the first 10,000 time steps where it collects the experience, and maybe the frequency affects exploration, which means that in the first initial 10,000 time steps, there could be they could have started all at the same reward.
So the weights are initialized after a certain like exploration.
Yes.
Okay.
I'll go again, sure. Have you considered for some of these tasks where there are longer stretches that don't need high frequency or low frequency actions, and then sometimes it does require very low frequency actions? Have you considered dynamically changing the frequency depending on any sort of information you get from the model?
Yes, that so the specific framing you're saying is going to be the future work of unsupervised skill learning of skills with multiple precision levels, and it's under the context with composite skills. Because in composite skills, it's made up of subtasks, which some tasks may require a different frequency to complete than other subtasks. And so that would be the.
Did you read Dator's paper? So Charles also was advised by Dator, my friend, who did his dissertation on that topic, which I think you would probably enjoy reading about. It's not like directly with skills, it's more general RL with dynamic frequencies like this, but there is a lot of work started in that domain, and if you want me to hook you up with him, I can.
Edward.
I see here you have black lines, and it says black lines represent reward and success rate.
Yeah.
Can you explain what that means again and why you chose those specific numbers, like 0.217?
So basically, what this essentially means is that when I graph the training curve, I had a certain reward, and that reward represents a certain success rate. So if your reward represents how good your policy is, then that reward would also represent that when your policy is that good, what is the success rate for this? And these numbers were specifically chosen was because in my training curve, majority of them were essentially the same or pretty noisy, and so essentially this is all the data I had for mapping reward to success rates. Does that answer the question?
So why did you choose these specific numbers? Are they like
These specific numbers were like the only numbers I had, basically.
Are they like a percentage of the success rate? Like past this reward, you have very high probability you succeed.
Yes.
And then it's like 50%, 100%, or something
Yes.
like that? Okay. Cool. Anything else?
Any other questions?
But in the second graph, why is the reward like all negative?
Oh, fetch, reach, dance is a distance task. It's basically you have a robot arm, you have a point, and the reward is the distance you get here. But distance is positive, so we do the negative reward instead. Alex.
Wait, each of these curves are just one run, or are they multiple? Like, do you have any initialization noises, or?
Yeah. So in my appendix right here.
Oh, right.
In my appendix right here, I test on different seats. And in the future, this is an work I would have to do is to test on more seats to make the precision horizon really solid. But yeah, I test on seat 40 to 42, and it yields the same results.
Alright, anything else? Rocky Cantor's having a big game about asking Nathan questions, anything? No? Alright, thank you. Good job, Nathan. we have finished the final research presentation. Good job, everyone. Those were excellent. I'm very happy with them. Now for the rest of the day, we're going to have a short break while the Rocket Camp goes and sets up their